Ever think about how your bank account stays up to date? Even if the bank system has like a glitch,
Right.
or how like a social media platform doesn't completely crash when millions of people are, posting and liking and doing all that stuff at the same time.
Yeah.
That's the magic behind the scenes of database replication and partitioning.
Uh-huh.
And you sent us some really, really fascinating sources
Yes.
that really dive deep into how these systems copy and distribute data. So let's get into it.
Yeah, most people don't realize just how complex it is
Yeah.
to make sure that your data is there and correct and that you can access it in, a fraction of a second, no matter how many other people are using the same app or whatever at the same time.
Yeah, it's like this intricate dance happening behind the curtain.
Yeah.
Right?
Yeah.
I'm super curious to learn about some of these specific techniques that are mentioned in these sources, like sloppy quorums and hinted handoff.
Oh, yeah.
They sound like they're from a sci-fi novel.
Yeah. Well, they do have these kind of intriguing names.
Right.
And they highlight the challenges of keeping data consistent when, it's spread across multiple servers. Like a group project where you're okay moving forward, even if one of your, team members is unreachable for a while, hoping they'll catch up later.
Yeah.
That's kind of the idea behind sloppy quorums. It's like allowing the system to operate, even if part of it's temporarily disconnected.
Right.
So there's a trade-off there between consistency and availability.
Right.
So yeah, it's a fascinating example of the kinds of decisions engineers have to make.
Okay, that analogy makes a lot more sense.
Okay.
So before we jump into the nitty-gritty, let's talk about why we even need replication in the first place.
Okay.
What's the big deal about having multiple copies of data?
Well, it boils down to three key benefits: fault tolerance, scalability, and latency.
Okay.
Fault tolerance is like having a backup generator for your house.
Okay.
If the power goes out, your lights stay on because the generator kicks in.
Right.
So in the database world, replication acts as that backup generator.
So if one server crashes, the other copies can take over and everything keeps running smoothly for the user.
Exactly.
So it's like having an insurance policy for your data.
Yeah.
To make sure it's always accessible.
Uh-huh.
Now, how does replication help systems handle massive amounts of data and users?
Right.
You called it scalability, right?
Scalability, yeah. Think of a popular social media platform.
Okay.
With millions of users all posting and liking and commenting all at the same time. You don't want one server trying to handle all that traffic and just, getting completely overloaded.
Right.
So replication spreads that load across multiple servers.
So it's like having multiple checkout lanes at the grocery store.
Exactly.
To keep things moving.
Yep.
Okay, so that brings us to the third benefit, which is latency.
Yes, latency is all about speed.
Okay.
Imagine you're trying to load a web page and it just takes forever. Replication can help by placing copies of the data closer to the users who need it. So, for example, a news website with readers all over the world.
Right.
They could have servers in different regions.
Okay.
So that articles load quickly no matter where you are.
So it's like having local branches of the library instead of everyone having to travel to one central location.
Exactly.
Okay.
Yeah.
Speaking of backups.
Yeah.
Our sources make a distinction between replication and backups.
Yes.
And it seems like they're doing the same thing, creating copies.
Right.
So what's the difference?
Well, think of it this way. Replication is for live availability.
Okay.
Like having a spare tire in your car.
Okay.
That can instantly take over if one gets flat.
Right.
You're always ready to roll.
Yeah.
Backups, on the other hand, are more like having a detailed blueprint of your car that you can use to rebuild it if it's completely totaled.
Okay. So replication keeps things running smoothly in real time. And then backups are there to help you recover from like a major disaster.
Exactly.
Got it. Now I'm curious to learn about the different types of replication.
Okay.
Is it just a one-size-fits-all approach, or are there different ways to copy and distribute data?
There are actually three main approaches.
Okay.
Single leader, multi-leader, and leaderless.
Okay.
And each has its own strengths and weaknesses and is suited for different types of applications.
Okay, that makes sense.
Yeah.
So tell me about single leader replication.
Okay.
Does that mean there's one server that's calling all the shots?
Exactly. In single leader replication, you have one designated server that acts as the leader.
Okay.
And it handles all the right operations.
Mm-hmm.
Any changes to the data have to go through this leader first.
Okay.
And then those changes are replicated to follower servers, which mainly handle read requests.
So you have one central source of truth
Right?
And then those changes are disseminated to the other servers.
Exactly.
What kind of real-world applications would use this model?
Your banking app. It needs to make sure that every transaction is recorded accurately.
Right.
So it uses synchronous replication, which means that the leader waits for confirmation from all its followers before it considers a transaction complete.
So that's why sometimes banking transactions can feel a little slow?
Right.
It's because the system is making absolutely sure that all the copies are perfectly in sync before giving you the green light.
Exactly.
Okay, so single leader is great for ensuring accuracy and consistency.
Yes.
What about multi-leader replication?
Okay.
What situations would benefit from that approach?
Multi-leader replication allows for more flexibility.
Okay.
Instead of having one server in charge, you have multiple servers that can accept writes independently. Think about Google Docs, where multiple people can edit the same document from different locations, even if they're offline.
So each person's device is essentially acting as a leader, keeping track of their changes.
Exactly.
And then those changes are merged later.
Right.
That's amazing. It's like having a team of authors working on different chapters of a book simultaneously.
Yeah.
Now that covers single leader and multi-leader.
Right.
What about this leaderless model? It sounds kind of like a recipe for anarchy.
Yeah, leaderless is maybe a little bit of a misleading term.
Okay.
It's not that there's no control.
Yeah.
It's more that any server can accept writes.
Okay.
This makes it incredibly fault tolerant.
Uh-huh.
If one server goes down, the system can just keep chugging along without missing a beat.
So it's like a highly resilient system that can handle pretty much anything you throw at it.
Yeah, pretty much.
What are some examples of databases that use this leaderless model?
You'll find it in popular distributed databases like Amazon DynamoDB and Apache Cassandra.
Okay.
These systems are designed to handle, massive amounts of data and traffic.
Right.
And they need to be incredibly robust.
Makes sense. Okay, so we've covered the why and the what's of replication.
Right.
I'm ready to get a little bit deeper. How are these changes actually propagated between servers?
Right.
Is it as simple as copying and pasting, or is there something else going on?
It's a bit more nuanced than that.
Uh-huh.
There are a few different approaches, each with its own pros and cons in terms of efficiency and flexibility.
Okay, let's break them down.
Okay.
Our sources mentioned something called statement-based replication. It sounds like that method has some limitations.
Yeah.
What's the deal with that?
Statement-based replication is a pretty straightforward concept.
Okay.
The leader basically records the SQL statements that it executes.
Okay.
And sends those exact statements to the followers.
So it's like sending instructions instead of the actual data.
Right, like sending instructions instead of the changed data.
Okay.
But it can be really inefficient, especially with complex statements or large amounts of data. And it can be prone to inconsistencies if you're using functions that generate different values on different servers.
Oh, okay.
Like imagine if you had a statement that included a random number generator. Right. The leader and the follower could end up with mismatched data.
So you'd be replicating the instructions but potentially getting different results on different servers.
Exactly.
Not ideal. What's a more efficient way to handle things?
Well, most modern databases use a technique called write-ahead log or wall shipping.
Okay.
Think of the wall as like a detailed journal that keeps track of every change made to the database.
Okay.
Instead of sending those bulky SQL instructions, the leader replicates this log to the followers, who then replay the changes to bring their copies of the data up to date.
Oh, so that's much more efficient because you're only sending the essential information about the changes, not the full SQL statements.
Exactly.
Makes a lot of sense.
Yeah.
Our sources mention some specific examples like MySQL's binary log and PostgreSQL's wall files. Right. So I'm guessing those are just specific names for the same general concept.
Yeah, they're just different implementations of the same basic idea.
Okay.
Yeah.
Are there any other approaches that go beyond wall shipping?
Yeah. There's also logical log replication, which is even more flexible because it captures changes at the row level instead of just the entire statement. This means you can actually replicate data between different database systems.
Wow.
Like from MySQL to PostgreSQL.
That's powerful. So it opens up a lot of possibilities for mixing and matching databases.
Yes, definitely.
Okay, so we've talked about how the changes are propagated.
Right.
Now, how do these systems make sure all the copies are synchronized?
Okay.
Do they all have to be updated at exactly the same time?
That's where we get into the concepts of synchronous and asynchronous replication.
Okay.
Synchronous replication, as we talked about with the banking example.
Right.
The leader waits for confirmation from all its followers before it considers a write-complete asynchronous replication. The leader doesn't wait.
Okay.
It just sends the changes and moves on.
So the followers are always playing catch-up.
Right. There's always going to be some lag with asynchronous replication.
Right, because the leader isn't waiting for confirmations from the followers before moving on.
Exactly.
So it's a trade-off between speed and accuracy.
Right.
Depending on the needs of the application.
Mm-hmm.
But you mentioned earlier that there are some potential challenges that come with having multiple copies of data floating around, right?
Right. Replication is not a magic bullet.
Okay.
It comes with its own set of complexities, especially when it comes to keeping things consistent.
Right.
And handling potential conflicts.
Okay. I'm all ears.
Okay.
Our sources mention something called replication lag.
Yes.
What exactly is that, and why is it a problem?
Replication lag is the delay between when a change is made on the leader and when it's reflected on the followers.
Okay.
So with asynchronous replication, remember, the followers are always playing catch-up.
Yeah.
There's always going to be some lag.
Okay, so what kind of headaches can this lag cause?
Well, imagine you update your profile picture on a social media site.
Okay.
But when you refresh the page, you still see your old picture.
Ugh, yeah.
That's because your request might have been routed to a follower that hasn't received the update yet.
So it's like the system is playing tricks on you.
Right.
Our sources also talk about monotonic reads as another potential issue.
Yes.
Can you explain that one?
Monotonic reads mean that as time progresses,
Okay.
you should only see newer data,
Okay.
never older data. It's like reading a book.
Yeah.
You wouldn't expect the pages to suddenly jump back to an earlier chapter.
Right. Right.
Right. So
you're saying that replication lag could cause a situation where you see a news article on a website, refresh the page, and suddenly the article's gone.
Exactly.
That would be super confusing.
Yeah, and it can happen because your initial request might have been served by a follower that had the new article.
Right.
But then your refresh request might have been routed to a different follower that hadn't caught up yet.
Okay, so replication lag can lead to some strange and frustrating inconsistencies.
Yes, definitely.
What are some ways to deal with these issues?
Well, one option is to stick with synchronous replication.
Okay.
For those really critical operations where consistency is absolutely paramount.
Right.
Like financial transactions.
Yeah, where accuracy trumps speed.
Exactly.
Okay. But what about applications where a little bit of lag is okay?
Right.
Are there any other solutions?
Well, you can use strategies like last write wins.
Okay.
Where the system just picks the update with the latest timestamp.
I guess that works if you're not overly concerned about losing the occasional update.
Right.
But it seems a little risky.
Yeah, it can be.
What about using timestamps to ensure those monotonic reads that we talked about?
That's a good strategy as well.
Okay.
If you assign a timestamp to each write operation, you can make sure that users only see data up to a certain point in time.
Okay.
Even if there's some lag behind the scenes.
Okay, so it helps to maintain a consistent timeline for the user.
Exactly.
So there are ways to manage replication lag and ensure a reasonable level of consistency, even with asynchronous replication. Yep. That's good to know. Our sources also mention another challenge. Conflict resolution.
Yes, conflict resolution.
Yeah.
This is a particular problem with multi-leader replication.
Okay.
Where you have multiple servers independently accepting writes.
Right, because now you have the possibility of two servers making conflicting changes to the same data.
Exactly.
How do these systems handle that?
Well, there's no one-size-fits-all solution that works for every situation.
Okay.
But there are a few common strategies. Sometimes you can try to prevent conflicts from happening in the first place.
Okay.
Like setting up clear rules about who can edit what data.
Right.
Or using unique identifiers to prevent duplicate entries.
So it's like setting up a system of checks and balances.
Exactly.
Okay. But what if conflicts are unavoidable? What then?
Well, one simple approach is that last write wins strategy that we mentioned earlier.
Right.
You just pick the update with the latest timestamp.
Right, but we already talked about how that can be a bit risky.
Right, it can be.
So what are some other ways to handle those conflicts?
Some systems will use unique IDs for each write operation.
Okay.
Which can help determine the order of events more accurately.
Uh-huh.
Others try to merge conflicting values if possible.
Okay.
Imagine two people editing different parts of a document.
Right.
Their changes could be merged together seamlessly.
Yeah, that's a neat solution if the data lends itself to merging.
Right.
But what if it's something like a number that can't be easily combined?
Right. In those cases, some systems might record the conflict and let a human decide how to resolve it.
Okay.
Or they might have custom logic that's tailored to the specific application.
Okay, so conflict resolution can get pretty complex.
Yeah.
And it often requires a combination of automated strategies and human intervention.
Right.
There's one more challenge I want to ask you about.
Okay.
Network partitions.
Yes.
Our sources make them sound like a nightmare for replicated systems.
Network partitions are definitely one of the trickiest problems to solve in a distributed system. Imagine a cluster of servers happily replicating data, and suddenly the network connection between some of them gets severed.
So they're like islands that are suddenly cut off from the mainland.
Oh, exactly.
What happens to the data in that situation?
That's where things get messy.
Okay.
Each isolated group of servers might continue accepting writes.
Right.
But those writes won't be replicated to the other groups. And when the network connection is eventually restored, you're left with conflicting versions of the data, and figuring out how to merge them can be a nightmare.
So it's like each group is writing its own version of history.
Right.
And then you have to reconcile those different versions when they're reunited.
Exactly.
That sounds like a recipe for disaster.
Yeah.
Are there any ways to deal with these network partitions and minimize the potential chaos?
Some systems use techniques like sloppy quorums and hinted handoff to try to keep things running smoothly during a partition.
Those terms are back.
Yeah.
You mentioned them earlier, but I'm still a little fuzzy on what they actually mean.
Yeah.
Okay. Can you break them down for me?
Sure. So with sloppy quorums, a server can accept a write, even if it can't reach a majority of the other servers.
Okay.
So it's kind of like leaving a note saying, hey, when you get back online, make sure to copy these changes.
Right.
So it helps to improve availability.
Okay.
But there's a risk of inconsistencies because you're making decisions without having a complete picture of the data.
Right, so it's a calculated risk.
It is.
Okay, what about hinted handoff?
Hinted handoff is a way to temporarily store information about writes that need to be propagated to other servers once the network connection is restored.
So it's like leaving a message for those disconnected servers saying, don't worry, I've got your updates safe and sound. I'll pass them along when you're back online.
Exactly.
It seems like managing replication is a delicate balancing act.
It is
with a lot of factors to consider. But we're not done yet. We've covered replication in detail, but now we need to tackle another essential technique for managing massive data sets.
Right.
Partitioning.
Partitioning, yeah. That's all about organization and efficiency.
Okay.
Like taking this giant, unwieldy database and dividing it into smaller, more manageable chunks.
Right. It plays a crucial role in helping databases handle massive amounts of data without breaking a sweat.
Yes, it does.
Okay. I'm ready to dive into the world of partitioning.
Okay, so think of it this way. Instead of having one massive library that's just impossible to navigate, you have a network of specialized libraries, each one focusing on a specific topic.
Right.
That's what partitioning does for databases.
Okay, that analogy really helps. So instead of one giant database, you're creating a collection of smaller, more focused ones.
Exactly. And just like having specialized libraries, this brings a bunch of benefits. The first one is scalability, which is crucial when you're dealing with massive amounts of data.
We talked about scalability in the context of replication.
Right.
But how does partitioning help systems handle all that data?
Imagine you have multiple librarians.
Okay.
Each responsible for a specific section of the library.
Okay.
They can manage the books much more efficiently than if one person had to handle the entire library alone.
Right. Yeah, that makes sense.
So partitioning allows you to spread the data across multiple servers.
Okay.
Just like those librarians managing different sections.
Got it.
Precisely. And this lets you scale horizontally.
Okay.
You can just add more servers as your data grows.
Okay.
Distributing the load and preventing any single server from getting overwhelmed.
Our sources had some great real-world examples.
Yeah.
Like a social media platform with millions of users.
Right.
They could partition their user data by geographic location.
Exactly.
Storing data for users in North America on one set of servers, European users on another, and so on.
That's a perfect example.
Okay.
It means that user activity in one region doesn't slow down the entire system. Right. Each region's servers can handle their own load, keeping things running smoothly for everyone.
And they also mentioned an e-commerce giant partitioning its product catalog by category.
Yeah, that's a good one.
So electronics, clothing, books, and so on would each have their own dedicated partitions.
This is super helpful for managing a huge product catalog.
Right.
It allows teams to focus on specific product categories and ensures that one team's updates don't accidentally impact the performance of another team's products.
Okay, so partitioning clearly helps with scalability.
Yes.
But how does breaking a database into smaller pieces actually make things faster?
Think about searching for a specific book in a library.
Okay.
If you know it's in the science fiction section, you don't waste time browsing through romance novels or cookbooks, right?
No, you go straight to the relevant section.
Exactly.
And narrow down your search.
That's exactly how partitioning works. When you execute a query, the database only needs to search the relevant partitions, ignoring the rest.
Okay.
This means it has to scan way less data, resulting in much faster response time.
It's like searching for a needle in a haystack, but you've divided the haystack into smaller piles.
Exactly.
Makes sense. The examples in our sources really help me understand this, like a banking system partitioning customer transaction data by account number.
Yeah.
When a customer requests their transaction history, the system only needs to look in the partition for that specific account.
Exactly. There's no need to sift through millions of transactions from other accounts.
Makes sense. And a music streaming service could partition its library by genre.
Right.
So when you're in the mood for jazz, it can instantly pull up the jazz partition and spare you from wading through all the heavy metal.
Exactly.
That would definitely improve my music listening experience.
Yeah.
So we've covered scalability and performance, but our sources highlighted another major benefit of partitioning: availability.
Right. Availability is all about making sure your system stays up and running, even when things go wrong.
Right.
Partitioning makes this possible, because even if one part of the system goes down, other parts can keep operating.
We've talked about fault tolerance in the context of replication.
Right.
But how does partitioning contribute to this?
Remember our library analogy?
Yes.
If one section of the library is closed for maintenance or has an issue, you can still access the other sections.
So even if one server holding a partition fails, other servers holding replicas can step in.
Exactly. Combining partitioning with replication creates an incredibly resilient system.
Okay.
For example, a global online retailer could replicate each partition across multiple data centers in different regions.
So if one data center has an outage, other data centers can keep serving customers without missing a beat.
Precisely. That's the power of combining these techniques.
Okay.
And a financial institution could do something similar with customer data.
Right.
Making sure that a server failure doesn't prevent people from accessing their accounts.
Okay, partitioning definitely seems like a must-have for building resilient systems.
Yeah, it's pretty important.
So we've seen how it helps with scalability, performance, and availability. It's like a trifecta of benefits for managing massive data sets. But before we dive into the challenges, I'm curious to learn more about the different strategies for actually partitioning a database.
That's a great point. Just as there are various ways to organize a library, there are different ways to partition a database.
Okay.
Our sources highlighted two main methods: partitioning by key range and partitioning by hash of key.
Okay, key range partitioning sounds pretty intuitive.
Yeah, it's a pretty common approach.
Does it involve dividing the data based on some kind of order?
Yes, exactly.
Yeah.
Think of it like arranging library books alphabetically. With partitioning by key range, you define specific ranges of keys.
Okay.
And each range is assigned to a particular partition.
So in a customer database, you could partition by last name.
Right.
Customers with last names starting with AG would go in one partition, HN in another, and so on.
That's a classic example.
Okay.
Or a time series database, which stores data over time.
Okay.
Could be partitioned by date ranges.
Got it.
So data for January 2023 would be in one partition, February 2023 in another, and so on.
Okay, that makes sense.
Yeah.
It's like organizing the data chronologically.
Exactly.
Now, what about partitioning by hash of key?
Okay.
That sounds a bit more technical.
It is, but bear with me.
Okay.
Imagine a function that takes any input, like a customer ID or a product name, and spits out a seemingly random number within a specific range.
Okay.
That's basically what a hash function does.
So you're assigning a unique code to each piece of data.
Exactly.
Yeah.
And with partitioning by hash of key, you use this hash function to determine which partition the data goes into.
I'm starting to see how this could work.
Okay.
Our sources talked about partitioning player data in an online game by hashing the player's username.
That's a great use case.
Okay.
It ensures that players are distributed evenly across partitions, regardless of their usernames.
And they also mentioned an e-commerce platform using this to partition orders during peak shopping seasons.
Right.
That would help to balance the load across servers when everyone's trying to buy things at the same time.
It's all about making sure no single partition gets overloaded.
Right.
Now, both key range partitioning and hash partitioning are effective techniques.
Uh-huh.
But just like with replication,
Right.
they also come with their own set of challenges.
Right, there's always a trade-off. What are some of the common issues that crop up with partitioning, and how do engineers address them?
One of the biggest challenges is dealing with skewed workloads.
Okay.
This is when certain keys are accessed way more frequently than others.
Our sources called this the hotspot problem.
Yeah, hotspots, it's a common problem.
What are some strategies for dealing with these hotspots?
One really clever technique is called consistent hashing.
Okay.
It helps minimize data movement when you add or remove partitions, which can be a big problem with traditional hashing.
So it helps maintain a balanced distribution of data even as the system changes.
Precisely. Another strategy is pre-splitting partitions.
Okay.
It's like anticipating which keys are going to be popular and allocating more resources to them in advance.
So you're creating more partitions for the high traffic areas.
Exactly.
To prevent them from becoming bottlenecks.
Exactly. It's like having extra checkout lanes at the grocery store.
Yeah.
For those times when everyone seems to need avocados at the same time.
Okay, good analogy.
Now, besides hotspots, another tricky issue is managing secondary indexes.
Can you remind me what secondary indexes are again?
Of course. Secondary indexes are basically lookup tables that let you quickly find data based on a field other than the primary key.
It's like having a card catalog in the library.
Yeah, exactly.
That lets you find books by author or genre in addition to the title.
Right, but when you've partitioned your database, managing these secondary indexes gets a bit more complicated.
Because now you have to distribute the index information across all those different partitions.
That's right. There are a couple of ways to handle this.
Okay.
One approach is partitioning by document.
Okay.
Where each partition has its own complete secondary index.
So it's like each section of the library having its own separate card catalog.
Precisely. The other approach is partitioning by term.
Okay.
Imagine, instead of a complete card catalog in each section, you have separate card catalogs for different genres, authors, or subjects.
So if I want to find all the science fiction books, I'd check the science fiction card catalog, which would tell me which sections to look in.
That's it. In this approach, each partition only indexes a subset of terms.
Okay.
It can be more complex to manage.
Right.
But also more efficient for certain types of searches.
Okay, so managing secondary indexes across partitions requires some strategic planning.
Yeah, definitely.
But it seems like we're just scratching the surface of the complexity here.
We are.
Our sources also talked about something called rebalancing.
Ah, yes, rebalancing.
Which sounds like it could be a major headache.
Rebalancing is essential.
Okay.
But it definitely adds another layer of complexity. It's like rearranging the furniture in our giant library.
So as the data grows or the system changes, you need to adjust the partition.
Exactly. Rebalancing is necessary when your database grows.
Okay.
And some partitions become overloaded, while others have plenty of space. It's also important when you add or remove servers from your system.
So it's like adding or removing bookshelves in the library as your collection expands or contracts.
Precisely. In both cases, you need to rebalance the partitions to ensure a balanced distribution of data and workload across all the available servers.
I got it.
There are a few different strategies for doing this.
Okay, tell me about them.
One approach is to start with a fixed number of partitions, like having a set number of bookshelves. You can pre-allocate a large number and distribute them across your servers.
So you're essentially planning for future growth by having those partitions ready to go.
Exactly. Another approach is dynamic partitioning, where you split and merge partitions as needed.
So you're kind of adding new bookshelves or consolidating existing ones based on your current collection.
Exactly.
I like the flexibility of that approach.
Yeah.
What's the third strategy?
It's called proportional partitioning.
Okay.
This is where you assign partitions to servers based on their capacity.
Okay.
So a more powerful server would get more partitions.
Okay.
Just like a larger section of the library would have more bookshelves.
Okay, that makes sense.
So you're matching the resources to the demands.
Right.
Now, regardless of which strategy you choose, our sources emphasize the importance of minimizing data movement and service disruptions during the rebalancing process.
Right.
Why are those two things so important? Well, moving large amounts of data between partitions can take a lot of time and resources.
Right.
And you definitely don't want to take your database offline or slow things down while you're rebalancing.
Yeah.
Think about trying to rearrange a library while it's still open to the public.
Yeah, that wouldn't be very popular with the patrons.
Right.
So it's all about making the rebalancing process as smooth and invisible as possible.
Exactly. There are a couple of ways to achieve this.
Okay.
One is to automate the process as much as possible using tools and algorithms that can intelligently move data between partitions without requiring manual intervention.
Okay.
The other is to perform rebalancing during off-peak hours.
Right.
When there's less demand on the database.
Right. So it's like rearranging the library after closing time.
Exactly.
Smart. Now that we've covered the ins and outs of rebalancing, what about request routing?
Okay.
How do these systems know where to send each request when the data is divided into all these partitions?
That's a crucial question.
Yeah.
Without efficient request routing, the benefits of partitioning would be lost.
Right.
Imagine sending someone to the library without telling them which section to go to.
Right.
They'd have to search the entire building to find the book they're looking for.
That would take forever. So how does request routing work in a partition database?
There are a few different mechanisms that our sources described.
Okay.
Let's start with key range routing,
since
we've already discussed key range partitioning.
Okay. I remember that data is divided based on ranges of keys.
Right.
So how does routing work in that context?
Key range routing examines the key in the request and figures out which partition contains keys within that range.
So if I'm looking for customer information for someone with the last name Smith, the system knows to route my request to the partition that contains last names, starting with S.
Exactly. It's a simple and efficient approach, especially for queries that involve searching within a range of keys.
Now, another method is hash routing.
Right.
Which uses the same hash function we talked about earlier for partitioning data.
Exactly.
So it applies that same hash function to the key in the request. And the resulting number tells it which partition to contact.
Precisely. It's like using that unique code as a map to locate the data.
Right.
This is very efficient and ensures a balanced distribution of requests across all the partitions.
Those two methods seem pretty straightforward.
Yeah, they are.
What about directory-based routing? How does that work?
Directory-based routing involves having a central directory that keeps track of which partitions are assigned to which servers.
So it's like a master directory at the library that tells you exactly where to find each book.
That's a great analogy.
Okay.
When a request comes in, the system consults this directory to find the right server and then forwards the request.
That sounds pretty convenient.
It is.
But what happens if the directory itself goes down?
That's the main drawback of this approach.
Okay.
The directory can become a single point of failure.
Right.
To mitigate this risk, you typically replicate the directory itself so that there's always a backup ready to take over.
Right, so there are trade-offs to consider with each approach.
Yes, always.
But it sounds like directory-based routing offers a lot of flexibility.
It does. It's easy to move partitions between servers without having to update all the applications that interact with the database. Right. You simply update the directory and the system handles the rest.
Okay, so we've covered how requests are directed to the right partitions. I'm ready for the grand finale. What's the last benefit of partitioning that we need to discuss?
The final benefit we'll explore is parallel query execution. This is where partitioning really shines because it allows the system to work on different parts of a query at the same time, dramatically speeding up the process.
Our sources described it as being like a team of librarians searching different sections of the library simultaneously.
Exactly.
That's definitely faster than having one librarian search the entire library alone.
Imagine a query that needs to calculate the total sales for a specific product.
Okay.
With partitioning, each partition can calculate its own sales, and then the results are combined to get the grand total.
It's like dividing a big task into smaller pieces and having multiple people work on them at the same time.
Precisely.
Much more efficient.
This is super important.
Okay.
When you're dealing with large data sets and complex queries.
Okay.
Because it allows you to leverage the power of multiple servers.
So partitioning not only helps with scalability, performance, and availability, but it also allows for parallel processing, which boosts performance even further. It's like the ultimate tool for taming those massive data sets.
Yeah.
Now that we've explored both replication and partitioning,
Right.
I'm curious to hear your thoughts on how these techniques work together in real-world systems.
That's a great question. It's important to remember that these concepts are not mutually exclusive.
Okay.
In fact, they often complement each other perfectly to create truly robust and scalable data systems.
Right, they're like two sides of the same coin.
Exactly.
Replication provides that redundancy and availability, while partitioning ensures that the data is managed and distributed efficiently.
Exactly. And when you combine them, you get a system that can handle massive amounts of data, withstand failures, and respond quickly to user requests.
It's like a well-oiled machine with all the parts working together in perfect harmony.
It is.
It's pretty amazing to think about all this complexity happening behind the scenes.
Yeah.
Every time we use an app or visit a website.
It really is a testament to the ingenuity and creativity of the engineers who build these systems. They're constantly pushing the boundaries of what's possible with data.
So as we wrap up this deep dive,
okay,
what are some key takeaways you want our listeners to remember?
I hope they understand that replication and partitioning are not just fancy technical terms.
Okay.
They are essential solutions to real-world challenges of managing data at scale.
Right. They're the unsung heroes of the data-driven world, making sure our digital lives run smoothly and seamlessly.
Exactly. I also hope they appreciate the fact that there's no one-size-fits-all solution.
Right.
The best approach depends on the specific needs of the application and the nature of the data.
So the balancing act between various factors like consistency, performance, availability, and complexity.
Precisely. And finally, I hope they come away with a sense of awe at the ingenuity and complexity of these systems.
Yeah.
It's easy to take technology for granted.
Right.
But it's worth taking a moment to appreciate the incredible feats of engineering that make our digital lives possible.
Well said. And on that note, I think it's time for us to wrap up this deep dive. We've covered a lot of ground today.
We have.
And I'm sure our listener has plenty to ponder.
I hope so.
We encourage you to keep exploring these topics on your own.
Yeah.
There's a whole world of fascinating details and intriguing challenges waiting to be discovered in the realm of data management.
Absolutely.
So, until next time.
Yes.
Keep diving deep and stay curious.
Sounds good.
Yeah, it really is mind-blowing when you think about it, right? All this intricate machinery.
Yeah.
All this stuff happening behind the scenes just so we can, browse the internet, shop online, connect with friends.
Right. It's like a hidden world of data.
Yeah.
Constantly being copied, shifted, and sorted.
Right.
And the really impressive part is that it's all designed to be completely invisible to the user.
Right.
Like, we just expect things to work instantly, and we get frustrated if they don't.
Which is understandable.
Yeah.
Right? Nobody wants to wait for a web page to load or, worry about their data.
Right.
But I feel like we've only just scratched the surface today.
We have.
Are there any other interesting details from our sources that we haven't touched on?
Well, one thing that stood out to me was the discussion of how these systems are actually implemented in the real world. It's one thing to understand the concepts, but it's a whole other challenge to actually build and maintain these systems at scale.
Right, because in theory, things always work perfectly.
Right.
But in practice, you always have unexpected issues and edge cases and...
Exactly.
Yeah.
And our sources touch on some of the trade-offs that engineers have to make when they're choosing specific technologies and approaches.
Right.
For example, there's no single best database for every situation.
So it's like choosing the right tool for the job based on the specific needs of the application.
Exactly.
Does that mean engineers have to constantly learn new technologies and adapt to new challenges?
Absolutely. The world of data management is constantly evolving.
Right.
New technologies emerge, new challenges arise, and engineers need to stay ahead of the curve.
It's definitely a dynamic and exciting field.
It is. Speaking
of exciting, I was particularly intrigued by the discussion of sloppy quorums.
Oh, yeah.
You explained it really well earlier, the group project analogy. But I'm wondering, are there any real-world examples of how this technique is used?
Oh, definitely. Sloppy quorums are used in a lot of systems where high availability is paramount.
Okay.
For example, some online gaming platforms use this technique to make sure that players can continue playing even if there's a network issue or a server goes down.
Right, because imagine the frustration if, like, a game suddenly froze because one server was having a problem.
Right, exactly.
Using floppy quorums helps to keep the game running smoothly,
Right.
even if there are some temporary inconsistencies in the background.
Exactly. It's all about prioritizing the user experience.
Right.
And speaking of user experience, one of our sources made a really interesting point about the importance of monitoring and performance optimization.
Right, because it's not enough to just build these systems.
Right.
You need to make sure that they're running smoothly and efficiently.
Exactly.
What kind of monitoring tools and techniques do engineers use to keep these systems humming along?
There's a whole ecosystem of tools and techniques dedicated to monitoring and optimizing data systems.
Okay.
They track everything from server load to query response times to network latency.
Wow.
They even use machine learning algorithms to predict potential issues and proactively address them.
So it's like having a team of digital doctors.
Yeah.
Constantly checking the vital signs of the data systems.
It's a great analogy.
Right.
And just like doctors, data engineers need to be able to diagnose problems quickly and accurately to prevent any major disruptions.
Yeah, I'm starting to realize that data engineering is like a never-ending quest for efficiency.
It is.
Right. Reliability, performance.
It is a constant challenge because as data volumes grow and user expectations increase, engineers need to find new and innovative ways to keep things running smoothly.
Absolutely. So I think our listeners have gotten a really good overview of the key concepts of database replication and partitioning today.
I hope so.
But where can they go if they want to learn more?
There are tons of great resources available online.
Okay.
There are blogs, articles, online courses,
Okay.
even open source projects that people can contribute to.
Oh, wow.
And of course, there are always new research papers being published.
Right.
Pushing the boundaries of what's possible in data management.
Yeah, it's a constantly evolving field.
It is.
So there's always something new to learn.
Always.
And that's what makes it so exciting.
Exactly. If you're fascinated by data and the challenges of managing it at scale, then this is a fantastic field to explore.
Absolutely.
And who knows, maybe some of our listeners will become the next generation of data engineering wizards.
Right.
Conjuring up even more innovative solutions to the data challenges of the future.
Well, on that inspiring note, I think it's time for us to wrap up this deep dive.
Okay, sounds good.
We've explored the intricate workings of database replication and partitioning.
We have.
From the high-level concepts to the nitty-gritty details.
Yeah.
We've discussed the different flavors of replication, the challenges of keeping data consistent,
right,
the power of partitioning for scalability and performance, and the importance of monitoring and optimization.
It's all important.
And I think along the way, we've also highlighted the incredible ingenuity and dedication of the engineers.
Yes.
Who build and maintain these systems.
They are the unsung heroes.
They are.
Of the data-driven world.
Right. They're making sure that our digital lives run smoothly and seamlessly.
That's right.
So to our listeners, we hope this deep dive has sparked your curiosity.
Yeah.
And inspired you to explore the fascinating world of data management.
Please do.
Even further.
Keep learning.
So until next time, keep diving deep. Stay curious. And remember.
Yes.
Behind every seamless digital experience, there's a symphony of data working its magic.
That's a great way to put it.